Fracture mechanism. First, before we start, I would like to ask if Angel Cernescu is around. Anybody knows him from Romania? Right, so that's the second speaker of the session. So if he doesn't come, we will shift.
Enough time for discussion.
Well, plenty of time. But in that case, we might as well shift the second speaker, and so it will be you, Simon. Okay, you will start at 12. So for the moment, we have Giovanni, who is going to talk about heat energy. Right, half an hour? Well, total, right?
Okay. Thank you for your kind introduction. Good morning. My name is Giovanni Meneghetti. I come from the University of Padua in Italy. And this work was prepared in cooperation with my colleague Mauro Cotta. I am going to talk about the use of the heat energy dissipated in a control volume surrounding the crack tip to correlate the crack propagation data. And in the end, we will show that the crack acceleration due to excessive elasticity can be accounted for by the use of this heat energy dissipated by the material. So, the outline of my presentation, first of all, the short introduction and motivation for this work, and then I will talk about the theoretical background concerning the evaluation of such average heat energy loss at the crack tip, and then I will talk about how to determine the structural volume where the energy has to be averaged. Then I will show you the experimental results, first in a classical way of presenting them, that is the crack propagation rate versus the range of the mode 1 stress intensity factor, and then I will present the same data versus the averaged energy at the crack tip, and then I will draw some conclusions. So, first of all, we know from the literature, many researchers wrote the energy balance at a point of a material subjected to fatigue loadings. We know that we have to spend some mechanical energy to input into the material to induce crack initiation and then propagation. Such energy splits into two. Some energy is stored inside the material and it is responsible for damage accumulation leading to initiation and then propagation of the crack. But some of this energy is dissipated as heat. As a first point, of course, looking at the energy balance, our attention is kept by these energy terms because this energy term is the one responsible for fatigue damage accumulation. But I will show in a while that this is quite difficult to measure, at least in a simple way. That is why researchers in the past brought their attention to the mechanical input energy or to the heat energy density per cycle. So, concerning the damaging energy stored inside the material, which is the true responsible for damage accumulation in a metallic material, we know the papers of Kilmot, Kaletan and Blottin, and also we looked at this energy. Concerning the heat energy, we have proposed to use it as a fatigue damage indicator, even if such energy is not by nature the fatigue damage. It is just an indicator, a useful indicator of fatigue damage. But I will talk about this in a while. And then the input mechanical energy, which is the area of the stress-strain hysteresis loop, has been used for example, by Ellin in his well-known book, where it is interesting, in my opinion, to note that 20 years ago he stated that because of measurement difficulties with regard to heat loss, Q, the energy associated with damage, EP, can be related to the supplied mechanical energy, W. And he used the mechanical energy as a fatigue damage indicator. But now we can measure the specific heat loss in a quite simple way with a non-contact measurement system, like, for example, an infrared camera. Now, why should we use the thermal energy in fatigue studies? First of all, I would like to state again that energy dissipation is not by nature the fatigue damage phenomenon, as it was pointed out very clearly by Professor Wong in France more than 20 years ago, because we all know that the fatigue damage, the physical mechanism is crack nucleation followed by crack propagation. In fact, it has been demonstrated in the literature that we can measure some temperature rise of a material subjected to a fatigue test, even if the stress level is below the fatigue limit. So heat energy might be dissipated even below the fatigue limit. Now, I want to show you these results that we presented in the low cycle fatigue conference in 2003. We measured the three forms of energy involved in fatigue by testing specimens made of an austempered ductile iron. So we started with a static test, and this is the energy expended to break the material in a static test. It is nothing but the area under the static two-stress, two-strain curve. And then we performed the fatigue tests in the low cycle fatigue, and we measured the total mechanical edge energy expended up to fracture. And you see here such an energy plotted versus the total number of cycles to failure. You see that the total mechanical energy is an increasing function of the number of cycles to failure, but this is not a new result. It had been found many years before, in 1966, by Halford, who performed such kind of tests, and we simply found nicely the same slope of such a curve, about 0.33 that Halford found in 1966. Now, we measured also with a special technique the heat energy dissipated by the material, and so for a given total number of cycles to failure, we had measured the total mechanical energy expended to break the material. We measured the heat energy dissipated during the fatigue test, so by difference we could estimate the energy stored inside the material to up to fracture. And you see here that the mean value of the total energy stored inside the material is in good agreement with the energy expended in a static test. Now, which is the problem? You see here that for a fatigue life of only 100,000 cycles, the total energy to fracture the specimen is about 10 to 7 kilojoule per cubic meter. Most of such an energy is dissipated as heat, and the stored energy is about 2 orders of magnitude lower than the total energy, the total mechanical energy expended during the fatigue test. This means that if we want to measure the energy stored inside the material as a difference between the total mechanical energy expended and that released as heat, our measurement will be affected by great uncertainties, because we have a very big quantity, we subtract a quantity which is of the same order of magnitude, so the result of our calculations will be affected by great uncertainties. So that is why we proposed to use the heat energy dissipated as heat as a fatigue damage indicator. Now, we have recently summarized a great number of experimental results of fatigue tests conducted on plain and bluntly notched specimens made of a stainless steel material. It is a 304 low carbon steel. Either strain-controlled fatigue tests or stress-controlled fatigue tests are reported here. We tested bluntly notched specimens, of course, notch effects, which are not accounted for by the nominal net section stress amplitude. But if we plot this data all together using the heat energy released as heat, you see that all the data collapse into a single scatter band, which has a scattering index more or less equal to that of single test series. So we can say that the heat energy could correlate with fatigue lives. Now, we have no cracked specimens here, smooth and bluntly notched specimen. The reason why I am showing you this figure is because we will use this figure later on. So we have this energy synthesis at a load ratio equal to -1 for our material. Now, the motivation of the present work is to study the crack propagation from a crack started, consisting of a very sharp notch, and we want to use the average heat loss to correlate the crack growth data. So the idea is sketched here. We use as a fatigue damage indicator the specific heat loss, but as we know that the notch becomes very sharp, or if we have a crack, like in this case, Norbers taught us that the fatigue-related quantity should be averaged in a properly defined material structural volume, where the process zone takes place. So, in formulas, we have to average the heat energy loss inside such a structural volume, so we have to perform such an integration. This is the typical situation that we observed in the laboratory tests. We have to define the size of the structural volume, and we have to define the procedures how to evaluate the average heat energy. So now we look at these two problems, the evaluation of the average heat loss, Q star, starting from temperature measurements performed in the laboratory, and then we have to evaluate the structural volume size RC, because we have the volume size here in our fatigue damage parameter. Now, starting from the first point, the problem is like this. We have a crack, and the first hypothesis is that the heat is extracted from QC only by conduction. We made some experiments in the laboratory. Of course, heat dissipation occurs by conduction, convection, and radiation, but we proved that the heat conduction is by far the most active mechanism to extract the heat from the crack tip. So we suppose that heat conduction occurs through the boundary of QC. All testing parameters are defined, and so we can evaluate the average heat loss by integrating the specific heat flux through the boundary of the structural volume. This means that we need to evaluate the thermal field in a polar coordinates, and we have to evaluate the temperature gradient exactly along the boundary of the structural volume. But when we perform such measurements in the laboratory, of course the mean temperature increase due to heat dissipation has another contribution, which is the thermoelastic temperature oscillation superimposed to the mean temperature increase. So what we typically measure in the laboratory is a signal like this. If we consider the ith pixel in our infrared camera video, we see that here the temperature starts to increase, of course, at the beginning of the test due to heat dissipation, but the mean temperature signal has another component, which is the thermoelastic temperature signal, which is superimposed. But we need the mean temperature signal here to estimate the energy dissipation, because thermoelasticity is a reversible exchange between mechanical and thermal energy. So we have to remove this contribution from our calculations. So this is just a short video to see. You see the flashing light at the crack tip. We are here, the mean temperature has stabilized according to the thermal boundary condition of our tests, and you see the flashing thermoelastic signal superimposed to this. Now, if we perform a pixel by pixel temperature averaging, we can calculate quite easily this mean temperature signal, and this can be done by commercial softwares sold with the infrared camera, and then after that we can evaluate the gradient of the thermal field to evaluate the heat the mean energy loss. So this quantity is the one appearing in this formula. Now, we have now to define how big is the structural size surrounding the crack tip to complete our evaluation. We made some hypotheses. The first one is that the structural volume size RC is a material property for a given applied nominal load ratio, and the averaged energy inside such a volume for a given fatigue life is a characteristic value independent from the geometry of the stress riser. This is a very classical hypothesis which has been done in the past many times, but typically concerning notches evaluated at the fatigue limit. It is assumed, the second hypothesis, that the circular, that the size of the shape, of the structural volume is a circle surrounding the crack tip. Other choices might be possible. Now, in our case, unfortunately, in the near threshold condition of the crack, the thermal rise close to the crack tip was very small as compared to the thermal accuracy of the available infrared camera, so we could not calibrate the size of the structural volume at the threshold conditions. Therefore, we calibrated the size of the structural volume at a lower fatigue life and precisely equal to 10 to 5 cycles and not at the threshold. So, to determine the size of the structural volume, I have to present now our experiments, and then I will go back to the formula to evaluate RC. We took the material we had tested in the past, which is a hot rolled 4 mm thick stainless steel material, 304 low carbon. We polished the surfaces of the specimens, and we black painted one specimen's surface, while the opposite specimen's surface was monitored by means of an optical microscope. So the crack starter was a sharp notch with two different notch opening angles and a reduced notch tip radius of 0.1 or 0.15 millimeters. We performed the fatigue tests under a load ratio of -1, and we monitored the crack length by means of a digital microscope. On the opposite surfaces, we monitored the temperature field by means of an infrared camera. The infrared camera operated at a frame acquisition of 200 Hz, and we achieved a resolution of about 20 micron per pixel using a spacer ring. And then we used the commercial software to analyze the videos taken from the laboratory. So this is the setup. We have the infrared camera looking at one specimen surface. On the opposite surface, we have the digital microscope. So the digital microscope allowed us to monitor the crack population, to measure the crack length, and to single out the crack tip, so that we could report the crack tip from the digital microscope images to the infrared camera image. This is the infrared camera view of one specimen on one side, and this is the digital microscope view on the opposite side. We have the crack tip here, which was reported here from the digital microscope view, and we have the structural volume size. The size is not defined yet. So let us look at a specific experiment. We repeated this kind of experiments changing these parameters, but let us look at an individual experiment so that I can present you the procedure. In this specimen, we have a total crack length of about 9.8 millimeters. The range of the stress intensity factor at the crack tip in this experiment is 32.7 megapascal per square root meter, and the number of cycles to failure is 69,000 cycles. So let us keep in mind this number, 69,000 cycles. Now, this is the typical videos that we collected from the laboratory. You see the thermoelastic effect. This is stiffness. We have some displacements to compensate. After motion compensation, we have a fixed image with respect to the infrared camera, and we have the flashing signal close to the active. All these videos were taken at a frame rate of 200 Hz. Now, if we go back to the characteristic energy-based fatigue curve of this material I have shown you before, and we enter with the fatigue life of our packet specimen, we come up with a characteristic energy of 0.66 megajoule per cubic meter cycle, and this is the characteristic energy for a given fatigue life. Now, if we go back to our cracked specimen, we have its life, we have the characteristic energy for that life. So the problem is to find the structural volume size such that the average of the energy inside that volume is 0.66 megajoule per cubic meters. This was the procedure, and we could conclude that the size of the structural volume is 0.65 millimeters. This is the procedure. Now, we repeated such procedure with 4 specimens. The first one is the experiment I have just presented you. We repeated these experiments with other specimens, and by averaging the structural volume size, we concluded that a mean value of 0.52 millimeters can be assumed in this case. Now, to evaluate the average energy, I have shown you before that we integrated the thermal flux to the boundary of the structural volume, so we had to go through these pictures. This is the crack tip. We evaluated at different angles the thermal flux, and we integrated this curve. So these are the diagrams we had to produce to perform our calculations. So now we have a procedure to evaluate the average energy, and we have an estimation of the size of the structural volume where energy must be integrated. We performed additional standard experiments with the crack propagation monitoring, so we produced the curves, crack length versus the number of cycles for different applied stress levels, and we calculated the mode 1 linear elastic stress intensity factor for each crack length. In view of this, we applied the peak stress method to speed up the calculations. We presented this method about 10 years ago, and we were inspired by the Japanese school in this case. The concept is this one. If we produce a finite element mesh with a given mean size of the finite elements, in order to evaluate the stress intensity factor right at the crack tip, we need just to evaluate the singular linear elastic peak stress at the crack tip. We need to know the average finite element size adopted in the analysis. If we multiply the linear elastic singular stress at the crack tip by the mean size of the finite element size to the power of the stress singularity exponent, which is 0.5 for a crack, and we multiply all this by a calibration constant which depends on the order of the shape functions adopted, we can estimate K with an approximation of about approximately more plus or minus 3%. So we applied this procedure to rapidly evaluate the stress intensity factor for our propagating crack, and this is the final result. The crack propagation rate versus the range of the mode 1 linear elastic stress intensity factor. What we can see here, we distinguished our experimental data with 2 simple symbols. The circular symbols are those data which comply with the conditions of applicability of the linear elastic fracture mechanics that we know from standard textbooks. The X symbols are relevant to those experimental data which do not comply with the condition of applicability of linear elastic fracture mechanics. So we have 2 vertical bars here. On the on the left-hand side, all data comply with linear elastic fracture mechanics on the right-hand side, all data do not comply with linear elastic fracture mechanics. You see that a Paris curve, of course, can be determined with a scatter band for the data appropriate to apply the linear elastic fracture mechanics, but at higher ranges of the stress intensity factor, we can note some crack acceleration with respect to the trend of the Paris curve, which was attributed to the excessive plasticity according to the literature, for example, the works by Professor Tanaka. Now, if we change the crack driving force from the linear elastic stress intensity factor to the averaged energy in structural volume, you see that all data, both those which comply with the linear elastic fracture mechanics and those which show the crack acceleration in terms of stress intensity factor, collapse into a single scatter band where the scatter index is the same or even lower than that in terms of linear elastic stress intensity factor. So, in conclusion, we use the specific energy per cycle averaged in the structural volume to correlate the crack growth rates. The size of the structural volume was defined by equaling the average energy in cracked and plain specimens, and this was the final value. When the crack growth data are presented in terms of range of the stress intensity factor, crack acceleration could be observed, but if the same data are plotted in terms of average heat energy, crack acceleration is accounted for in a single scatter band. In the future, I would like to correlate the thermal energy with the G integral, which we know it is able to account for crack acceleration due to excessive plasticity. And also we have assumed a circular shape of the structural volume, but of course the same technique can be applied if different shapes are assumed. This is a very well-known shape proposed, for example, by Professor Taylor, but also might be the size of the reversed plastic zone at the crack tip and so on. So thank you. Sorry, thank you.